So we are going to look at how to integrate a of x divided by b of x dx, where a of x and b of x are both polynomials in x. So for example, we might have the integral of x over x squared plus 5 dx in a simple case, or maybe something much harder like x to the 7 plus 3x squared plus 5 divided by x to the 10 plus 3x to the 8 plus 2x minus 1 dx. We're going to do this in a way that effectively treats these polynomials and these quotients of polynomials, I should say, in the same way. So there are going to be 3 steps to this method. Step 1, we do a polynomial division. So we take that quotient a of x over b of x and we write it as q of x plus r of x over b of x. Now this is a bit of a confusing language now because I've called a of x over b of x a quotient in the sense it's a fraction, but we can also refer to the nice part we get out of the division here, q of x as the quotient and r of x here as the remainder. That's the language you might have used if you've done this at A-level maths, and some people do these by long division here, and there are many ways of actually doing this division. So for example, if I had x cubed plus 2x plus 1 over x plus 1, I could easily here just factorize out the x plus 1 from the top and get x squared to make it x cubed. Then I'd have a plus x squared, so I need to take off an x squared to make sure I've got 0x squared, so I'd subtract the x. Then I realize I've got a plus 3 here to make it plus 2x, and then so it's not quite a factorization. I'm going to end up here with plus 3 if I multiply out those brackets, so I'll subtract 2 to get what I want here. If you want to do that just by an ordinary polynomial long division, that's also fine. But the point here is we can write a quotient x squared minus x plus 3, and then this remainder of 2, which would be still over the b polynomial x plus 1. And what I can do now then is just integrate each of those terms separately, right? So the first one becomes x cubed over 3 minus x squared over 2 plus 3x, and the second one 2 times log mod x plus 1. They're both techniques from A-level integration. I'm not going to go through all of the basics of integration in this video. I'm going to point you to other resources as needed. Okay, but this basic idea of doing this polynomial division will be the same for our more complicated polynomials as well. So the key bit of theory we want here is that, you know, if I've got say I've got a 10th order polynomial divided by a 7th order polynomial, what I end up with is a cubic for the quotient part, because 10 minus 7 is 3. That's just using the rules of indices, and then the remainder polynomial will always have a lower order or lower degree than that of the denominator b of x. So in this case it would have order at most 6. The highest power would be x to the 6. So basically that first step of the process, doing that polynomial division, quotients out a nice polynomial that we can integrate easily, and then leaves us with a polynomial divided by a polynomial, but where the numerator is of a lower order than the denominator, and then that's something we can work on in steps 2 and 3. Not too hard to show that you can always end up with something of lower order in the numerator, by the way. If it was of higher order, you can easily show that you can do further quotienting out of terms until you get something of lower order. So now we've done that division, we can focus just on the second integral here, the remainder divided by b of x, and we're going to express that using partial fractions. We need to start with a lemma here. If you haven't come across that term, a lemma is just a result that we are going to assume in proving the result. So we can prove the lemma separately. Actually, this lemma here is kind of a big lemma. It's kind of equivalent to the fundamental theorem of algebra, but what it states is that every polynomial with real coefficients can be factorized as a product of linear or irreducible quadratic factors, possibly raised to positive integer powers. So what I mean is I can take a polynomial like x cubed plus 1 and I can write it as x plus 1 times x squared minus x plus 1. X plus 1 is a linear polynomial, right? It's just a linear term, and x squared minus x plus 1 is an irreducible quadratic. It's a quadratic whose discriminant is less than 0 in GCSE notation. If we solved that equal to 0, it would have no real roots. Okay, but I can do that with any polynomial with real coefficients. So I can take this much more complicated polynomial I've written down here, and I can write it as irreducible quadratic squared, x squared plus 1 squared, linear 2x minus 1 cubed, multiplied by another linear term. And in principle, there might be a lot more quadratics, lots more different powers, lots more linear terms if I've got a much higher order polynomial. And of course, the numbers might not come out as nicely as this, but it's always possible to do that. Now, I'm not going to prove that here in this video. It's not too hard to do. You do just need to know a little bit about complex numbers, but we'll put that proof in another video separately, because it is also such a big and important result in its own right. Even though it's a lemma for the purpose of our proof here, it deserves its own sort of video as a very big theorem in its own right. But what does this mean for what the partial fractions representations can look like? Well, let's take an example. So if that bx polynomial is x plus 1 times 3x minus 5 squared times x squared minus x plus 1 times x squared plus 1 cubed, then the terms that I would get, well, each set of sort of partial fractions terms corresponds to one of these factors. So for the x plus 1, as you know from A-level maths, you would just get a term a over x plus 1. Now when you've got something like 3x minus 5 squared, what you get is b over 3x minus 5 plus c over 3x minus 5 squared. Again, you know, a, b, c, all of these capital letters are just ordinary real numbers here. And if I had a higher order term, like, you know, if it was 3x minus 5 cubed or 4, or to the 4th power, I'd have extra terms like a constant over 3x minus 5 cubed and 3x minus 5 to the 4 as well. So you get the highest one and all of the ones lower than it. And for the irreducible quadratics, we get the same sort of thing, but on the top of the irreducible quadratic, we might get a linear term now, right? Because all I have in these partial fractions representations is that the numerators are going to be lower order than the denominators. So for the quadratics, you can get linear. For the linear ones, you can only get constants. But the same idea applies here. So for x squared plus 1 all cubed, I've got one term with x squared plus 1. I've got another one with x squared plus 1 squared, and another one with x squared plus 1 cubed. So again, showing that partial fractions representation is exactly as it is might require just a tiny bit more work. In particular, I think showing that, for example, you know, that this is exactly the form you get for the higher order powers. But again, I'm going to sort of siphon that off to be part of a different topic. This is this theory of partial fractions that you see a bit of at A-level, but it's never really done completely. Most teachers don't even end up writing down this case. It's quite complicated. You usually just learn one or two cases and then apply them. So here we're seeing a much richer theory of partial fractions. But really, the important thing to notice here is that what it means is that the only types of terms that we can get out here are things like a over bx plus c to the n, i.e. a linear term raised to an integer power, positive integer power, or I can get like a linear term over an irreducible quadratic to a positive integer power. And in this case, of course, it could be that either a or b are 0 for the quadratic, but that's our general form. So if we can integrate all of those types of terms, then we'll be able to integrate our r of x over b of x, and then we'll be done. So the final step here is going to involve computing each of these integrals. So in step 3, we're going to compute those integrals, and we'll look at a few different types then. So the first type is the easiest, just a linear denominator raised to some power. If that power is 1, in the easiest case, we've just got 1 over x plus 6 dx. Well, as long as you've got as far as doing differentiating a natural log function, and then reversing that as an integral, you'll know you get here log of the modulus of x plus 6 plus c. Again, I'm not going to go into why all of these integral results are true. That's for separate videos. And similarly, if we have 3 over 2x plus 5 cubed, say, or something like that, just a constant over a linear factor to a higher power, then we can just write that as something like 3 times 2x plus 5 to the minus 3, and then use the reverse chain rule here, usual integration of increasing the power by 1 and dividing by the new power, and then we also divide by 2 because of the 2 inside the brackets here. So again, I'm going to assume you've seen these reverse chain rule integrals before. You could alternatively do this by substituting u equals 2x plus 5, and in all of these cases, basically substituting u equals the denominator will be another way of solving those integrals. That's the easy case. So let's look at the harder cases. In the second case, we will have an irreducible quadratic denominator, but let's say it's not raised to any power. So we might just be lucky with these. So for example, I could have 2x minus 1 over x squared minus x plus 1 dx. That's of this very special form where the numerator is the derivative of the denominator, and because x squared differentiates to 2x, minus x differentiates to minus 1, and 1 differentiates to 0. Again, this is an A-level result that we know that this then integrates to log of the modulus of the denominator f of x here, again plus a constant of integration. If I've missed the constants of integration here and there, I'm not too worried in this video. Sort of a lucky case, but it's an important one for how I'm going to go about something harder here. So if I start with the integral of 5x plus 3 over x squared minus x plus 1 instead, actually all I'll do is I am going to do a bit of arithmetic to split that integral so that it has, so we've got one that's like 2x minus 1 on the top. So if I just force a 2x term on the top, well, it's actually 5x. So to force that, I'll need to multiply outside by 5 over 2. So this is now still equivalent to having 5x. And I just need to make this fraction here plus 6 over 5 then, because 6 over 5 times 5 over 2 is 3. So these are equivalent. And now you can see this 6 over 5, instead of thinking of it as 6 over 5, I can have it as 6 over 5, I can have it as minus 1 plus 11 over 5, and then, so I'll get an 11 over 5 here, and if I also combine that with the 5 over 2 outside the integral, I end up with this constant 11 over 2. But the point here is in the algebra, what I've managed to do is write it as a constant times this integral that we can do easily using this result, plus another integral, which is just now 1 over the irreducible quadratic. And so I've simplified this to say all I need to be able to do now is to know how to integrate constant or 1 over my irreducible quadratics. And all of those sorts of integrals can be dealt with by first completing the square in the quadratic in the denominator, and then using kind of a trig or kind of similar substitution. I'm not going to go through all the different cases here because I've made another video which is titled Integrating the Reciprocal of a Quadratic, made many years ago now, but I'll link it in the description below, and you can see that you can deal with those cases pretty straightforwardly with things. You get things like sort of arctan integrals. So the final case to deal with is where I've got 1 over a quadratic, but that quadratic, it's an irreducible quadratic, raised to an integer power again. And in this case, we're going to start by completing the square. So whatever the quadratic was, I'll actually make sure it's now in the form 1 over x minus a squared plus b, all to the power of n. I can just complete the square in that quadratic. Then you see if I make this substitution, u equals x minus a over the square root of b, I end up with an integral that in the denominator here has just u squared plus 1 to the power of n, where I have pulled out a constant of b to the power of n here and just called it capital A on the top of the integral. But the point I'm trying to make here is that by this substitution, I can just change it to the form of something over u squared plus 1 all to the power of n. Notice, by the way, that if you're worried about this b being negative, it actually can't be negative if you want the quadratic to be irreducible. So in all the cases we're considering this is a valid trick to play. Right, so actually we can just do these integrals and we are done. So we'll start with the simplest case without it being raised to any power, so just 1 over x squared plus 1. We'll just remember that that integral is arctan of x. You can substitute x equals tan u if you want to, and do that. Hopefully you've seen that integral, or you can see it in another video. Now, instead of doing that integral, we can get to the x squared plus 1 squared one by actually integrating this first one by parts instead, using a trick of writing it as 1 over x squared plus 1 multiplied by 1. So I'll take the u as 1 over x squared plus 1 and the v primed as 1, and then differentiating 1 over x squared plus 1 gives minus 2x over x squared plus 1 all squared, and integrating 1 gives us x. So the integration by parts gives us u times v here, which is x over x squared plus 1 minus u primed times v, which gives us actually plus 2 lots of x squared over x squared plus 1 then, and that's just using the usual integration by parts formula that the integral of uv dashed dx is equal to uv minus the integral of u dashed v dx. Okay, so what you see here is that this integral on the right, if I make that the subject of this line, and remember that this first integral is actually arctan of x, that means that x squared over x squared plus 1 integrated is actually a half of arctan x minus a half x over x squared plus 1, again plus a constant of integration if you want, and that's just making this integral the subject of this line. Right, now this is very useful because you can write the integral 1 over x squared plus 1 dx in again a different way, as if I multiply top and bottom by x squared plus 1, then I get x 1 over x squared plus 1 all squared, and I can separate that into two integrals, x squared over x squared plus 1 all squared and 1 over x squared plus 1 all squared. And so again, making this right-hand integral the subject of this line, that means that this next integral that we're looking to be able to do, right, 1 over x squared plus 1 all squared, I can just write as 1 over x squared plus 1 integrated minus the integral of x squared over x squared plus 1 squared, right? But, well, we know how to integrate 1 over x squared plus 1. Obviously, it's arctan x. We've used that already. And then this other integral here is just the one that we've done by integrating 1 over x squared plus 1 by parts. It's kind of a sneaky trick here, right? So I can just substitute in the result we got here, half arctan x minus a half x over x squared plus 1, and that gives us this result then, that this next 1 over x squared plus 1 all squared integrated is a half arctan x minus a half x over x squared plus 1, again plus a constant of integration. Right, so that's kind of neat. We've been able to take our integral of an irreducible quadratic and turn it into the integral of an irreducible quadratic squared. Now, obviously, these higher power cases don't come up very often, and when they do, you can use something like Wolfram Alpha to do these integrals usually. But it's nice to know that we can, in principle, do them. And the way we would go about doing this for a higher power is that if we define in to be the integral with n as the power, so 1 over x squared plus 1 to the power of n dx, we can use a similar argument to establish what's called a reduction formula. And again, I've made another video about reduction formulae in general that I'll link below as well. But it establishes this reduction formula that says the nth integral here, if you like, is equal to 1 over 2n minus 2 times x over x squared plus 1 to the n minus 1, 2n minus 3 over 2n minus 2 times the n minus first integral. So it gives us this formula that takes us from the n minus first integral to the nth integral. So given that we've got I2 already, you see we can use this formula now to work out I3, I4, I5, etc. And the argument that establishes this reduction formula I'm going to leave as an exercise, but it follows exactly the same sort of algebra as we've done above, taking the previous case, integrating it by parts, and making the equivalence there in exactly the same sort of way. So, for example, if I want to get I3, right, that's 1 over x squared plus 1 cubed, right, I can just put n equals 3 into my reduction formula. So I3 is 1 over 2 times 3 minus 2 is 4, and then x over x squared plus 1 to the 3 minus 1, so there's a 2 there, and then this fraction just becomes 6 minus 3 is 3, and this 2 is 4, so that's 3/4 times I2, but I2 is the integral we've just worked out, right, the integral of 1 over x squared plus 1 squared. So this is a quarter x over x squared plus 1 squared plus 3/4 times a half arctan x minus a half x over x squared plus 1 plus a constant of integration, and so on and so forth. So once we've got that, we could do the same with I4, right? I could put I4 into my n equals 4 into my reduction formula, and where I get in minus 1, then I'll just put this result for I3. And so I can actually do this for any value of n. I could start with I8, and I'd have to work it out in terms of I7 and then I6 and I5, etc. But in principle, I can do it. So I didn't promise you at the start here that this would be a really neat and simple formula, of course. Why would you expect it to be? We're trying to integrate the quotient of any two polynomials. We're going to expect there to be quite a lot of different answers depending on the different cases here. But just to recap and review that, we've looked at how to integrate. We've looked at how to integrate the quotient of any two polynomials in 3 steps. So we start by doing a polynomial division, getting a neat quotient that's easy to integrate, and then a remainder polynomial which is of lower order than the denominator polynomial. We write that remainder polynomial over the denominator polynomial using partial fractions, noting that we can only get linear powers to linear factors to positive integer powers or irreducible quadratics to positive integer powers. We split that integral into many different integrals potentially if it's a large polynomial, and we just integrate each of those one at a time by a mixture of methods, all of which basically that come up in A-level maths and further maths. The first cases for the linear denominators are all contained in A-level single maths, and the quadratic cases come up in most courses for A-level further maths, although it might depend exactly which options you choose. Although the third type, the reduction formulae, don't come up in this form necessarily. Some people do study reduction formulae as part of further maths, depending what they're doing, but maybe not looking at these particular types of cases. So there we go. We have now, though, be very confident that given any polynomial divided by any other polynomial with real coefficients, that we can integrate it. Actually, in the end, although it's a bit messy and there's lots of different parts to it, you see we feel like we've got a really substantial result there. Lots of different avenues, we've covered all the different cases, and this is how we go about more rigorous mathematics. And I've left a few gaps in proofs for other videos, but so please do go and have a look at those if you want to as well. But I hope that's given you a good overview, and I hope you're now confident